Hello everybody, welcome. This is paper 1 from November 2023, time zone 1. Let's work through this and see what we can do. Alright, starting with question 1. Billy is a keen walker who keeps a record of his performance. The following table shows the time in minutes it takes him to walk 1 kilometer up hills with different gradients. The gradient of each hill is constant. And so here we have the gradient at different moments and the time it takes him to walk 1 kilometer. Question A asks us to find the equation of the regression line of t on g, and then part 2 of A asks us to describe the correlation between t and g with reference to the value of r and the Pearson's product moment correlation coefficient. Alright, so we've got two variables, gradient and time. We're asked to find a regression line. This one is, I think, pretty straightforward application. Let's go into spreadsheets and calculate a regression line. Turning over to the calculator, let's have a look. Spreadsheets. Let's put gradient, g, and t. You can always use x and y, and if you're more comfortable with that, that's perfectly fine as well. 15 and 20. And then let's put the values in 6.85, 8.42, 11.20, 14.49, and 17.88. Alright, values in, columns are labeled. Let's go ahead, menu, statistics, stat calculations, and here we have our linear regression. Tell our calculator where we put the x's and y's, press enter, and there we go. Okay, find the equation of the regression line of t on g. This is our slope, m, and b is our y-intercept. Let's return to the document for a sec and have a look. Okay, so find the equation of regression line of t on g. T on g, I'm going to look to the mark scheme after. I think potentially it might be a mistake if we write it in terms of y and x. So let's actually use the variables. So g, actually I'll write it in terms of y. No, let's write it like this. G is equal to 0.552, and then this would be x, but since this is our y and this is our x, we have g is equal to 0.552t plus 6.3, and it's 6.357, so we'll round it to 6.36. So normally this is what it would look like, hopefully not expanding on this more than we really need, but this would usually be y is equal to 0.552, and then this would be x plus 6.36. Gonna check the mark scheme just really quick to see what they are asking. A and B for an equation, A1 for correct values of A and B, A1 for an equation using these correct values. So it looks like they are using t and g. Whether we would lose marks if we wrote y and x, to be honest, is a little unclear in terms of the mark scheme, but for safety's sake, maybe not bad. Alright, second part, describe the correlation between t and g with reference to the value of r, the Pearson's product moment correlation coefficient. So going back to the calculator screen just for a sec, we see the correlation coefficient is 0.9939. So let's write out r is equal to 0.994 in this case, 3 sig figs. Alright. And actually, I'm going to write this out. They're asking us to describe it, and it is potentially a 2-mark question, so we need to state what this would mean. So r is equal to 0.994. This is A2. R is equal to 0.994, and this would be what's called a strong moderate correlation between, and then the two variables, gradient and time taken to walk. And then we could say 1 kilometer, but I think that's fine. Time taken to walk 1 kilometer. There we are. Alright. On Sunday, Billy intends to walk up a hill with a gradient of 13%. Part B, question B asks us to estimate the time it will take Billy to walk 1 kilometer up the hill. So we already have an equation linking the gradient and time. Here we have a gradient of 13%, so let's go ahead and just substitute that in. So gradient is already given percentage as this whole number of values. So let's write 13. 13 is equal to 0.552t plus 6.36. And since we have an equation with only one unknown in this case, we can go ahead and work this out algebraically or just end solve for t. I'm going to go ahead and do that. So let's go back to the calculator screen. Here we are. Calculator, menu, algebra, numerical solve, and 13 is equal to 0.552, let's call this t, plus 6.36, telling our calculator what we want to solve for t. The answer is 12.029. So let's write that as, going back to the document, t is equal to 12.0. So 3 sig figs once again. All right, estimate the time, 12.0 minutes. This morning, Billy walked 1 kilometer up a hill and it took 22 minutes. Explain why it would be inappropriate to use the equation found in part A to estimate the gradient of this hill. So here we are. Let's imagine we have this value and it takes him 22 minutes. One thing that we notice about this value is that we have a range of times from 6.85 all the way to 17.88, but this value of 22 right here is actually beyond the set of values of which we collected data for. So what does that mean? That means that we actually have what's called extrapolation. So just really quick summary here. If we have a set of values that we've collected data for, and then we go ahead and we create a line of best fit or some regression line, which models it to some degree, we can be potentially, if the correlation is strong, right? This is the other thing. If the correlation is strong, then we can be relatively sure that we can use this regression line to get some decent prediction. But if we're asking for points beyond this, then it gets a little risky because there's nothing to say that it's going to be linear or that it might not be an asymptote and just level off right here. There's nothing to say that this is going to continue on. So what we have here is extrapolation. It might not be appropriate because we're outside of the range of values that we have collected for. And let's go to the mark scheme to see what else we could potentially have. Extrapolation seems to be coming out okay. Alright, so here we are for C. Using the T on G regression line cannot always reliably make a prediction for G. I think that's a little vague actually. I wouldn't use that reliably. Extrapolation. No reason to assume this new hill has a constant gradient. That's interesting. Yeah, potentially. Could be some up and down kind of road. Yep, I guess for myself, extrapolation comes out most readily. Alright, not a bad question to start off. I would say working through this exam, one thing that is a little more unusual compared to others is the structure. Usually the exams might go from the least challenging to most challenging by and large. This one has some quite challenging questions relatively early on. But I guess that's one of the reasons the 5-minute reading time might come in handy. Okay, let's start with question 2. The Great Pyramid of Giza is the oldest of the 7 wonders of the ancient world. When it was built 4,500 years ago, the measurements of the pyramid were in Royal Egyptian cubits, REC. Victor reads online that 1 rec, or 1 REC, is equal to 0.52 meters, rounded to 2 decimal places. Write down the upper and lower bounds of 1 REC in meters. So we have 1 REC is equivalent to 0.52, and this is rounded to 2 decimal places. So let's work through this and see what we have. So we have 1 REC is equal to, let's write that, 1 R EC is equivalent to 0.52 meters, but it's rounded to 2 decimal places, so this value right here. And then if we ask ourselves the lower bound and upper bound, I'm going to write it right here. Lower bound, let's use a different color. The lower bound, what is the least possible value this could be if we are rounding to 2 decimal places? So again, we could have 0.51, and then what? If it's, let's say, 7, we round up. If it's 6, then we round up. And if it's 5, then we would round up. Anything below, if it's, let's say, 514,99999, we're rounding down to 0.514. But since we're rounding up to 0.52, our lower bound in this case is going to be 0.515. That's the absolute lowest it could be. Anything lower we round down, and then of course anything higher we're rounding up. The upper bound, let's work this out with a similar kind of logic, so 0.52, and what could this be? If it's 4, for example, we're rounding down. If it's 5, you might say, oh, okay, well if it's 5 we're rounding up, but let's extend this logic. If it's 4, we're rounding down. If it's 0.49, we're still rounding down. And we can extend these 99999 on into infinity, and then if we do, if it's 0.524,99999 all the way to infinity, essentially what we have is 0.525. So anything at 0.524,99999, or essentially 0.525 and less, we round down, and anything above 0.515 we round up. So write down the lower and upper bounds. Let's write this out in a way that they might like. Lower bound is equal to 0.515. Upper bound is equal to 0.525. You can write this as an inequality as well, as in x is greater than and less than, if you like. Alright. The Great Pyramid of Giza has a square base with side lengths of 440 REC and a height of 280 REC. Victor assumes that these two measurements are exact and that the Great Pyramid can be modeled as a square-based pyramid with smooth faces. So they're telling us square-based pyramid, 280, that's our height, and side lengths, which is a square base, so all equal side lengths for our pyramid. Find the minimum possible value in cubic meters. So the minimum possible value, that tells us that we should be using our lower bound in this case. So if we have 1 REC is equal to 0.52, but potentially it could be actually a little lower since we're rounding, let's use the lowest possible value to find out the absolute minimum volume of this pyramid. Okay, so let's go ahead and take a look. I'm hoping I have our formula booklet here so we can just look at it together, I suppose. Here it is. Let's go ahead to geometry. This is actually the new standard level formula booklet as opposed to the standard higher level. It's condensed, I suppose. Okay, so what are we looking for here? We are looking for the volume of a pyramid. Let's see. Volume of a prism. Volume of a right pyramid. There we are. Volume is equal to 1/3, or 1/3 area of the base, and then h is a height. So volume is equal to 1/3 AH, where A is the area of the base. Okay, let's write that down here. Volume is equal to 1/3 A, which is the area of the base, times height, the height of the pyramid. And we want to work with the minimum. So what do we have here? A few different ways that we can work this out. Let's try to simplify things as much as possible. Area of the base. Area of the base, if we're talking about some pyramid, or this, and let's not use that one. If we're talking about the pyramid, square base of 440 REC. So if we're talking about the side lengths, let's find the area of this base. Let's sketch it out. And not a bad idea to sketch if we have geometry, or geometry question. So this is equal to 440. But we know that it's 440 times 0.515, because this is the absolute minimum. So this is going to be one side length. Let's find the area of the base. 440 times 0.515. 440 times 0.515 is equal to 226.6. And I would recommend leaving your values like this instead of writing 22.7. Try to preserve all the accuracy that you can up until the final answer, where you would write in 3 sig figs. So intermediate steps, wouldn't recommend writing out in 3 sig figs. You'll have a little deviation in terms of level of accuracy. So if this is one of the side lengths right here, 22.6, the area of the base for a cone, for a cone, for a square, is going to be, well, side length 1 and let's say side length 2, which are equivalent. So let's go ahead and write out the area of the base. Volume is equal to 1 over 3, and then area is going to be 226.6, and then we can write this out as squared, but just for simplicity, 226.226. So that's the area of the base. And then we're asked, okay, what about the height? And the height, they tell us, is right here, 280. So if we've got some pyramid, I'm just going to draw something like this. Not going to go 3 dimensions, not exactly. But our height of our pyramid is equal to 280. But again, we want to use the lower bound of 0.515. Okay, 0.515 times 280 is going to be equal to 144.2. Let's keep all the accuracy as well, and let's write it out as 144.2. Okay, so it wasn't actually too bad, I suppose. Now let's just work it out on a calculator. So let's see, 226.6, square that value, times 1 over 3, times 144.2. Okay, quite a large value. Volume is equal to 2468106.051. Minimum possible value of the pyramid in cubic meters. If your calculator gave you this, they might write e to the 6. They would say plus e6 or something like that. It might be like 2.47 plus e to the 6, which is essentially saying 2.47 times 10 to the 6, where this calculator notation is saying, okay, well, times 10 to the 6. And this would be absolutely fine for 3 sig figs. If we wanted to write it out in this very long form with all of our digits, to 3 sig figs, we would write this as 2, 4, 7, and then 0, 0, 0, 0 point. Actually, we don't need that last point. If we want to write it out using scientific notation, if this is our decimal place right here, 1, 2, 3, 4, 5, 6 hops. And then we would get 2.47 times 10 to the 6 hops, or times 10 to the 6. Essentially, we're multiplying by 10 to the power of 6. All right, and that would be our minimum volume in meters cubed. All right, so potentially some of those rounding questions can be difficult, but somewhat formulaic, I suppose, as well, once you've seen a few. I'd recommend converting your units. Converting your units initially, I think, simplifies the process. All right. Okay, question 3. Consider the graph of the following function. F of x is equal to 16 over x plus x squared over 8 for x does not equal 0. And this is actually kind of important. X does not equal 0. If x is equal to 0, then we are dividing by 0, and the calculator explodes. You can't divide by 0. It's not a mathematically kind of consistent sentence in some kind of sense. It doesn't make sense. So to divide by 0. It's undefined. All right, part A says write down the equation of the vertical asymptote of f of x. Asymptotes can be vertical or horizontal. Just really quick. Here it is. Here is some xy coordinate grid. An asymptote can potentially be a vertical asymptote where we go off into infinity. So towards this direction, this would be our vertical asymptote where we go off into infinity. And we can also have a horizontal asymptote. Horizontal asymptote is what we rest at, essentially. You see horizontal asymptotes more so in something like exponential functions or something like this. The horizontal asymptote is what we approach but never reach. So, in this case, we're asking for the vertical asymptote of f of x. Vertical asymptote of f of x. Let's go ahead and see where we approach some line that we approach but never reach, and then vertically, not horizontally, so parallel to the y-axis. Let's go ahead and graph this to see what it looks like. So let's go to the calculator here. 16 over x plus, let's write another fraction, x squared over 8. All right, there's our function. Instead of zoom fit, just be cautious. Graph entry, Windows zoom. If we zoom fit, we lose a lot of detail here. Here it looks like there's something else. So sometimes zoom fit is going to be the quickest and it's going to be the easiest. But in this case, if we zoom out, we might get a better idea of what's going on in terms of asymptotes and so on, in terms of overall, I guess, level of detail, at least where it matters. So if we look for the asymptote, where do we go off into infinity? Actually, I should probably retrace that a little. If we do zoom fit, we see that you get a different idea. So where is the asymptote, the vertical asymptote? Right here on this vertical line, when in this case x is equal to 0. So let's go back to the document. So write down the equation of the vertical asymptote. In this case, they don't just want us to write 0, we need to write when x is equal to 0. Going back and trying to make sense of that algebraically, just really quick. If x is equal to 0, we have something undefined. But x can become very, very close to 0. So there are going to be points where we're dividing 16 by some super small number. And then in this case, we're asking, okay, how many times does this really massive, small number fit into 16? How many times? And of course, it can go like an infinite number of times. And so that's why we approach infinity. So as x becomes very, very small, we approach infinity. And we have this vertical asymptote, this line that we approach right here. All right. Often we're asking, okay, when does the denominator reach 0 for what value? In this case, it's just x, so when x is equal to 0, that's going to be our vertical asymptote. Here they're asking us to find f prime of x. That is to say, they're asking us for the derivative. 3-mark question, kind of nice. We've seen this before. It's quite often a question when they ask us to take the derivative. We have this x in the denominator. So let's go ahead and find the derivative. I'm actually going to go to the formula booklet just to show you that it is here. Here we are, calculus, our derivative. If we have something raised to the power of n and we want to take the derivative, multiply that exponent out in front and then reduce it by 1. So let's go ahead and get back to the document. So here we are. If we have f of x is equal to x of n and we want to find the derivative of x, what are we doing? We're multiplying this exponent out in front, but we are reducing it by 1. So let's use that logic here. But first, we need to take care of this x in the denominator. So let's go ahead. We have 16 over x plus x squared over 8. But we can't yet work with this x in the bottom. because it's not in the form of x to the n. So let's make sure that there is nothing in the denominator, no variables in the denominator. So let's rewrite this. F of x is equal to, let's keep the 16 out here, but we know that 1 over x is equivalent to x to the negative 1. 1 over x squared is equivalent to x to the negative 2, and 1 over x cubed, or even x to the n, is equal to x to the negative n. Whatever it is, if you have something in the exponent, a variable in the exponent, this is raised to the power of 1, we bring this up, and then we just convert this to a negative. Kind of helpful way to remember. So this is 16 over x becomes 16x to the negative 1. And then one last thing, I hope I'm not going into too much detail here, but 16 over x is the same as 16 times 1 over x, which is then equal to 16x to the negative 1. That's how that works algebraically. And then we have plus x squared over 8. Okay, now we're ready to take the derivative. So here's our derivative sign. Okay, let's take this negative 1, multiply it out in front. We're going to have negative 16x. It used to be negative 1. Let's subtract 1 from it. Now it's negative 2. Plus, let's do the same thing here. Let's take this 2, multiply it out in front. Let's even go the long way. Now it's going to be 2x. This used to be a 2. Take away 1. It's just x to the 1 over 8. And then, if you want, and I'd recommend, I guess, we can simplify this. 2x over 8 is just going to become x over 4. X over 4. 2x over 8, to be honest, I don't think you'd lose a mark for that. Alright, so a lot of these things are potentially procedural, and to be honest, it's a common enough question where we do have an x value in the denominator, where it should be something we're probably comfortable with, especially when they ask you to take a derivative. So common, they want to test the skill. It's just a very, very common question. All right, write down the interval in which f of x is increasing. The interval, so the bounds within which this function is increasing, or just simply going up. Let's go back to the calculator screen. So here we are. This was our kind of zoomed in portion, and we see it's going down here, and then it goes all the way down to negative infinity, goes to positive infinity, and then it goes up. We're not really sure what happens after that, so let's zoom out. Let's go ahead, window zoom, let's zoom out, and then we can see it's actually more or less like a quadratic. So window, zoom fit. So after this point, it is increasing. Let's find out what that point is. Let's go back into a little closer to where we were. The interval over which it's increasing. So it goes down, then it goes up to infinity, but this is like a clean break. It doesn't like suddenly inch up to infinity. It's a clean break. Negative infinity, then positive infinity. Still going down, but there's some point where it has its minimum. So let's find that. There's this point right here where it has its minimum. When x is equal to 4, and y is equal to 6. When x is equal to 4, it reaches its absolute minimum. It's done going down, and then it starts increasing, we saw, forever and ever and ever. So let's go back to the document for a sec. Write down the interval in which f of x is increasing. When x is greater than 4. The interval in which f of x is increasing. When x is equal to 4, so we don't write x is greater than or equal to 4, because when x is equal to 4, we're at a minimum. This is actually when the slope is equal to 0. And it's only when x is greater than 4 that we have this increasing. And that would be it, when x is greater than 4. What could we do? It's a 2-mark question. To be honest, I've actually seen the mark scheme in this case, and x is greater than 4, I believe, is actually enough. If we wanted to, potentially a sketch just to be sure. Something like this. And then label x is equal to 4, y is equal to 6 as some minimum. But x is greater than 4, the interval in which it's increasing. We're asked for an interval. That's kind of interesting. That means they want us to show inequalities. So when x is greater than 4, or less than infinity essentially. Let's see what they have in the mark scheme. Here we go. Okay, here we are. When x is greater than 4, or 4 to infinity, here if you look on the far right side it says A1, A1, which means 2 marks just for the correct answer. They are expecting some kind of inequality though. You can't just write 4, or x is equal to 4. You get A1 for 4, but for the inequality, the interval, that is to say the range in which this function is increasing. That's what they're looking for. Alright, so far it's been, I guess all things considered for an applications interpretations question, somewhat heavy on the algebra side. Here we are on number 4, and it's still, a little heavy in terms of algebra potentially. Alright, here we go. On the following Voronoi diagram, the coordinates of 3 farmhouses are A, 03, B, 83, and C, 813. Where distances are measured in kilometers. Each farmhouse owns the land that is closest to it, and their boundaries are defined by the dotted lines on diagram 1. Alright. To provide water to the farms, it is decided to construct a well at the point where the boundaries meet on diagram 1. So here is diagram 1. Write down the coordinates of this point. So to provide water to the farms, decided to construct a well where the boundaries meet. So this is the boundary line here, here's another boundary line here, and this is another boundary line. Where do they meet? They meet at this point right here. The coordinates of this point, this is at 4, and we may assume it's at 8. So they're just asking for a coordinate point. It meets at 4, 8. How could we be absolutely sure that this is the case? Boundary lines occur at the midpoint between these two. So if this is a y value of 13, and this is a y value of 3 at point B, distance between here is equal to 10. That means 5 above, 5 below. This right here is going to have an x value in this case, I guess of 10, I suppose, since we're just above here, but a y value of 8. And same here, this point is going to be halfway between as well. So between 0 and 8 is going to be the value of 4. And so if we put that together, the x value of 4 and a y value of 8. But for a 1 mark question, maybe it's wrong to assume, but maybe it is sometimes actually. But for a 1 mark question, you can potentially assume that they're going to give you clean integer values and not, let's say, fractions or anything like that. That would require further kind of computation. That is to say, we're just looking for something that we can see through inspection. That is to say, just by looking. If it was anything more, it would be computation, and we could imagine a 2 mark question. Alright, find the equation of the perpendicular bisector of AC. So the equation of a perpendicular bisector of AC. Perpendicular bisector means that if we have some line connecting AC, we are looking for the line that is perpendicular and that cuts this exactly into halves. So perpendicular bisector of AC, 3 mark question. Usually these are actually 4 mark questions, but I think it is possibly because we already have the midpoint here. So if this is a boundary point, we already have the midpoint here, so maybe that's where one of the marks comes from. Okay, so let's go ahead and work this out. Find the equation of the perpendicular bisector of AC. I'm going to go down here actually and write this out because potentially it could take up a bit of space. So here's B, And let's write down the coordinate points of A and the coordinate points of C. We're going to have to look back at what they were. 0, 3, and 8, 13. 0, 3, and 8, 13. Alright, if we didn't know the midpoint, we could find the midpoint. MAB. MAB is equal to the average of the x values. So this is x1, y1, x2, y2. This would be 0 plus 8 over 2, and the average of the y values, 3 plus 13 over 2. In this case, the midpoint would be, once again, 8 over 2, 4, and then 16 over 2, 8. There's our midpoint. So we've got a point on the line. Now we need to find the slope. We can find the slope or the gradient of AC, and then we know that this is going to be perpendicular, the perpendicular bisector. So we can use the negative reciprocal. So if we want to find the slope of the perpendicular bisector, let's first find the slope of AC. Alright. So, actually I shouldn't call this M because potentially that's our slope. So let's call it midpoint. Midpoint of AB. And now let's find M of AB, that is to say the slope. And we have y2 minus y1 over x2 minus x1. This is our slope, and it's given to you in the formula booklet as well. Might not be a bad idea to label these if you're unsure. It might help you structure things. So 13 minus 3 over 8 minus 0. And this is going to be 10 over 8 or 5 over 4. Okay, so we know that M, or MAB, is equal to 5 over 4. If we're looking for M perpendicular, we know what we're going to do is we're going to switch the top and the bottom, or take the reciprocal, 4 over 5, and then multiply it by a negative. So that would be our perpendicular. We know what MAB is. We're looking for the perpendicular to this line. Switch the top and the bottom, multiply it by a negative, or take the negative reciprocal. Alright, good. So we've got all the gradients we need. So we have y is equal to mx plus b. We know that m of this perpendicular bisector is negative 4 over 5. And we also know that it goes through the point 4, 8. So we've got a point on the line. We have an x value and a y value. Let's substitute those in. 8 is equal to negative 4 over 5. X is equal to 4 plus b. And you can end solve this, to be honest. It's not an insignificant amount of algebra, and you might actually save your time, or save some time. Let's actually, I'll work it out in the back end, but you might want to end solve, to be honest. Negative 4 times 4 divided by 5. Answer, alright, so we get an answer of b is equal to 4.8, or if we wanted to, as a fraction, this is b is equal to 24 over 5. Okay. Alright, that's good. It's kind of clumsy to mix fractions and decimals, so maybe we can write this out as y is equal to negative 4 over 5 x plus 24 over 5. If you work this out yourself and you got negative 0.8x plus 4.8, it's all the same. And the IB would actually be just as happy with either one, by and large. Okay, quite a fair bit of work for a 3-mark question, but there it is. Perpendicular bisector of AC. Alright, let's go on. An additional farmhouse D, 6.5, so now we're in diagram 2. An additional farmhouse D at point 6.5 is built on the land. The Voronoi diagram has been redrawn to show the new boundaries. The coordinates of the vertices of these boundaries are indicated on diagram 2. Okay. A wind turbine is to be built at one of the vertices. Okay, the vertices are the corner points. So if we're talking about vertices, we're talking about these points, the points where the boundary lines meet. The wind turbine should be as far from the nearest farmhouse as possible. So this is what's called like the toxic waste dump problem. The wind turbine should be as far from the nearest farmhouse as possible. By calculating appropriate distances, find the location of the wind turbine. This is plural, which is kind of interesting. And then hence write down the distance of the wind turbine to the nearest farmhouse. 4-mark question, not too bad, I don't think. So let's go ahead. We know that the wind turbine is going to be at one of these locations, and the gist of the toxic waste dump problem is that the idea is that these wind turbines make noise, and we want to put it as far away as possible from the farmhouses. And so, if we have an equal distance, essentially, it looks like we can exclude one as possible, one right away. This value of A, for example, actually let me do it the other way. So this is one where one turbine could be. And this, just by inspection, looks like something we could exclude, because this distance right here is shorter than this distance here, for example, just by inspection. But the question is, let me actually use some different colors. Oh no. Whoops. So if we're looking at this pink line or this red line, the question is which one is the greatest distance? So the red line signifies the distance between this farmhouse B and a potential turbine. And we also know that this is actually going to be equivalent from this as well. Let me just give a conceptual kind of explanation of the toxic waste dump problem. So all of these points, if we sweep out a circle, then there is the possibility that we want this turbine to be as far away as possible. And remember, the boundary lines are the equal distance, an equal distance to each of these places. So if we go back to this one right here and we sweep out a circle, we're asking ourselves, okay, which one of these is, let's say, the furthest away? Which one of these has the largest radius? Because each of these points are going to be, let's say, the boundary lines themselves will represent, I'm sorry, I'm just kind of mumbling through this. The boundary lines themselves will be equidistant. So if we're looking at point, this is now very messy. If we're looking at point D right here and point B, this is equivalent, this is equivalent, this is equivalent, and so on. The boundary lines represent an equal distance between two farmhouses. And then there's one point where they meet, and that's the edge of a boundary line. And this is the farthest essentially that we can get, where we're still an equal distance away from both. And same here, we're an equal distance away from both at this point and at this point, or rather at this point as well. So which one is going to be the largest? It is going to be the one with the circle, essentially, that has the largest radius. To simplify that even further, I suppose, what we can do is simply find the values where find the values that are the furthest away. So we can take away this point just by looking at it. It seems like it's pretty close to A. So we're really just comparing this point right here, and let's choose any other point. Let's choose this point right here. What we can even do is let's choose these 2 points. I think it'll be good. Okay, so 2 different things we can do. We can use the distance formula, but the distance formula is essentially the Pythagorean theorem. So let's actually just use the Pythagorean theorem. Here we go. So if we're at 6 and we travel to 11, we know we're going to have a base of 5. And similarly, if we're at 5 and we go up to 8, we're going to have a, what can we say, a height of this right angle triangle of 3. So by the Pythagorean theorem, we know that 5 squared plus 3 squared is equal to, let's call this x, is equal to x squared. And we can work that out. 25 plus 9 is going to be 34 is equal to x squared. We can end solve this, and x itself, you can leave this itself as root 34. Similarly here, let's write this out using the Pythagorean theorem. Here we go. So, this isn't nice. This isn't nice. So this is kind of finicky. Okay. So we know 1 is equal to root 34. Okay, so that's why it's a 4-mark question. If we're going from 9/11 to 6, what are we traveling? Well, this itself would represent 6 minus 9/11. And then we could square that, but I guess we could. And if we're at 5, for example, in our y value, and we go up to 1/16 over 11, then we can also represent this as 116/11 minus 5. And potentially we could put this into a calculator and write this out as a decimal. And that would be okay. Actually, that's exactly what I'm going to do. 6 minus 9/11, square that value. This is roughly equal to geez Louise, 3249 over 1. Okay. Essentially, it's just messy decimals, and it's us using the distance formula. So if we go all the way, and here's our distance between 2 points, x1 minus x2 squared plus y1 minus y2 squared, and then take the square root of all that. Okay, there's no getting around these kind of messy decimals. So here it is. Let's use the distance formula. Distance is equal to y1 minus y2. So if this is x1, y1, this is x2, y2. Alright, we have, just as it says here, 6 minus 9 over 11 squared plus 116 over 11 minus 5 squared. And let's see what we can do. 6 minus 9 over 11, square that value, plus 116 over 11, just working this out on the back end, minus 5, then we'll square that, and then let's take the square root of all of that business, and then it tells us that d is equal to 7.589, or just 0.759. So we have 1 as a messy decimal and 1 as a rather clean root. Let's convert this to a decimal, and this itself is equal to 583. So comparing these, this is the one that would be furthest away, and it suggests that we should build our turbine right at this location, right here. Wind turbine should be as far from the nearest farmhouse as possible. By calculating appropriate distances, find the location of the wind turbine. So essentially, just write out a distance formula just like this, or for example, if the numbers are clean, you can use Pythagorean theorem and construct triangles. By finding the appropriate distances, find the location of the wind turbine. The wind turbine should be at 9 over 11 and 116 over 11. That's where it should be. And write down the distance of the wind turbine to the nearest farmhouse. We found out that the distance was 7.59. Alright, so that one took quite a while. Sorry for the lengthy explanation for the Voronoi diagram. Little clumsy, I suppose. Okay, here we go. Let's recenter and move on. Okay. Question number 5 looks like a bearings question. Ron sails his boat from point R for a distance of 150 kilometers on a bearing of 120 degrees. To arrive at a point S, he then sails on a bearing of 38 degrees to point T. Ron's journey is shown in the diagram. So here's Ron. He sweeps through an angle of 120 degrees and then sets off 150. Sweeps through an angle from true north and then heads off again. Okay. Interesting question. Even more interesting, the first kind of bearings question that had shown up on these exams was from May 2023, the first time one had shown up even on specimen papers. And then it's kind of interesting that the second time it had shown up was right after on the next exam in May. So somewhat interesting. Find RST. Okay, find RST. What are they asking us to find? If we start at R, then we go to S, and then we go to T, they're asking us to find this value right here. RST. Also sometimes see this as RST, where you're looking for that middle angle. Just follow the points and you'll get there. Find RST. Here we have a situation where we're going to need to remember our angle pairs. So if we have two parallel lines cut by what's called a transversal, and let's say we have this as A and we have this as B. Whoops. We have this as B. If we know, for example, angles at a point sum to 180, and here we have two corresponding angles, this is B and this is B, we also know that A plus B is equal to 180 degrees, as these are equal to 180 degrees, and these two guys right here are equivalent. So A plus B is equal to 180. So let's use that. 120 plus what? Plus 60 degrees. And then 60 plus 38. Since this is a 2-mark question, let's write it out. 60 plus 38 degrees is equal to 98 degrees. We might even want to include this 120 plus x is equal to 180 to show how we found the 60. But I think this should be enough. So RST is equal to 98 degrees. 98 degrees. Point T is directly east of point R. Calculate the distance that Ron sails to return directly from point T to point R. So directly east means that we travel directly on a flat line. So again, if we have north, south, east, and west, to go directly east means that we don't have any kind of deviation north or south, directly east. Which actually is quite nice, makes this question super simplified. It was very nice of them to do that, I think. Point T is directly east of point R. Calculate the distance that Ron sails to return directly from point T to R. So Ron is going to head back this way. He's going to go back from T to R. And the question is, what is this side length here? We've already defined x, so let's call this z. Calculate the distance that Ron sails to return directly from point T to R. We have what looks like a non-right angle triangle. So again, we can either use sine, cosine, or area formula. Sine's always going to be the easiest. Let's try that out first. We're going to need an angle and its opposite side length. We already have one angle right here. If this is 120, then we know that this is a right angle, and this itself should be 30. 120, this is a right angle right here. This itself should be 30. If we know 30 and 98, we know that 30 plus 98, let's write it out here. 30 plus 98 plus whatever this is, and let's call this theta, I suppose, plus theta is equal to 180 degrees, because the angles of a triangle add up to 180. So working that out, you can end solve that if you like, would give us a value of 52 degrees. So let's add that to our diagram. Alright, so we know 3 angles of a triangle. Now the question is, do we have a situation where we have an angle and its opposite side length, and an angle and its opposite side length? And we do have those pairs. So we should be able to use our sine rule. Once again, our sine rule, A over sine A is equal to B over sine B. So let's write that in. We have 150 over sine 52 is equal to Z, we don't know what it is, Z over sine 98. And we can go ahead and end solve that. I'm going to work it out. Actually, no, let's work it out on the calculator. So let's go ahead. Calculator, it looks like I'm stuck in radians. Let's go ahead and change that to degrees. Menu, no, don't need to do any of that. Let's go ahead and end solve. Numerical solve. And let's go 150 over sine 52 is equal to, let's set up another fraction. Let's call it x in this case, is equal to sine 98. Of course we called it z, but for the calculator let's just leave it at that. Is equal to 188. So, returning back to the document, z, or the missing side length, is 188.5 to 3 sig figs, 189 kilometers. That's how far he needs to travel. And it's actually not a bad question, to be honest, making use of these co-interior angles, but otherwise not too bad. Alright, this is a pretty heavy question, and I think I'm going to need to charge my pencil after this, so maybe the last one, and then we'll stop it here, I guess, for now. Question 6, 4-mark question, so rather light. Consider the following function. H of x is equal to 2 over the square root of x minus 1 plus 1/2 for x is greater than 1. Find h inverse of 1. Find the domain of h inverse of x. Pretty heavy algebra. Often don't see this so much on applications interpretation. Interesting question all the same, but very kind of heavy algebra. Okay, let's work through it. Part A. Part A actually is not so bad. We're asked to find the inverse, h inverse of 1. So remember, we have a set of inputs and a set of outputs. And we have certain inputs like 0 or 0, 1, 2, 3, 4, something like that. And we have a function. In this case, it's h of x. And it will take those inputs and it will map them to certain outputs. In this case, we feed in a value of, let's say, 0 into this x value, and then we get something out in return. Maybe, in this case, if we feed in 0, we might not actually get an output. But if we feed in a value of, let's say, 4 or something like that, we will get a value. Or feed in a value of 2, for example, it looks like we'll get an answer of 2.5, for example. So we feed in value of 2 and out comes 2.5. This is our idea of a function. We have a set of inputs. The function is some kind of rule, which once we input, or we plug in those inputs, it gives us an output. And an inverse kind of does the opposite. you feed it in these values, and it will tell you what that original input was. So you can feed it those outputs, and it'll tell you what the original input was in that case. So this h inverse of 1, what they're saying is, if the output of our function was 1, what was the input? So here we know that the output in this case is 1. That is to say, the y value is 1. What was our input? And in this case, all we need to do is just write 1 is equal to 2 over x minus 1 plus 1/2. And then we can go ahead and end solve. So let's go ahead and end solve this for x. I'm going to go ahead and do that here. So looking back to the calculator screen, here we go. Menu, algebra, numerical solve. 1 is equal to, pretty intimidating question, or at least looks kind of like it. X minus 1 plus, we can write 0.5 or just leave it as a fraction. 1 over 2, and then ask our calculator to solve for x. And the value is 17, so not too bad. When they're asking us for an inverse, we're asked if the output itself, the output is 1 in this case, what was the input? And in this case, x would be equal to 17. Not too bad of a question. This is an extremely challenging question, at least I think. All right, consider the following function. We want to find the domain of h inverse x. So domain is usually the set of inputs. So if we have this function h of x, the domain is a set of inputs that we can feed into the function, and that they'll produce a set of outputs. And in this case, just looking at the function that we have now, the set of inputs, this is for h of x, the set of inputs would be limited because we can't have a 0 in the denominator, and the square root, we can't have like a -1, because we can't multiply some value by itself and get a negative, because something times itself, negative times a negative is a positive. So just looking at the domain of this h of x, there are some values that we can't actually put in. And that's what they're asking us here, but they're not asking us about h of x, they're asking us about h inverse, so the inverse of this. So usually the domain is a set of inputs that we can put into a function, and they'll have an output. If we're asked for the domain of the inverse, we're saying, what are these possible values that we can feed in, and that they'll produce some output. So how can we do this? H of x, we have inputs and they generate an output, but they'll only generate certain outputs. What are all of the outputs that are generated? If we know all of the outputs that are generated, then those outputs themselves must have an input. So let's find out the total collection of outputs. What are the total collection of outputs here? Because if we know if this thing, if h of x itself has an output, then we should be able to feed those outputs into our inverse and get back to an input. Get back to what was originally an input. Okay, so let's go ahead and try to find that. Let's go and look at our function. I think that's going to be the easiest way. All right, so here we go. Let's write out this function. So 2 over the square root of x minus 1 plus 0.5, or let's write it out as 1/2. All right, let's write out this function. Here it is. Okay, the set of outputs. So we're looking for the set of outputs that we could feasibly put into our inverse. And it looks like we can't put any negatives. We can't put any negative values because those don't have an output. We can't say, okay, what was the input? But it looks like we do have certain values that go all the way up to infinity. So any value up to infinity could potentially be an output of this original function, or an input for our inverse. But it looks like, and let's zoom out a little here, go zoom out, it looks like after a while we reach some kind of asymptote. And let's go graph trace. And just moving along here, we see as we move to the right and get larger and larger values, we approach some kind of asymptote. And we can even use graph trace, for example, and ask what the value is when we're at, I don't know, some massively large value. And it looks like we reach some asymptote when we have, let's say, in this case, 50 million, we're at a value of 0.5. So the set of outputs for this original function are all the way from positive infinity to 0.5. All the way from positive infinity to 0.5. So let's go back to this home screen once again, or the document. And I realize this looks a little messy right now, but what do we have? We have all the way from 0.5. We have inputs all the way from 0.5 all the way to positive infinity. And if that's the case, we should be able to plug in values from 0.5 to positive infinity into our inverse function, and they should give us some kind of output for our inverse function. Remember, inverse is reverse the inputs and outputs for a regular function. So all the way from 0.5 to infinity, we have some values that once inputted into our inverse will generate an output. So find the domain, that is to say the set of possible inverses, the set of possible inputs for our inverse. Well, in this case, it looks like the domain of H inverse x is greater than 0.5 and less than positive infinity. It's not equal to 0.5 because we have this asymptote, and the asymptote is something that approaches a point but never reaches it. There it is. Yeah, that's what I would say. There's potentially a more maybe complex kind of algebraic explanation, but I think that's as best as I can do in terms of simplifying it without getting into some more kind of muddy waters. All right, let's go on and look at question 7. All right. An athlete on a horizontal athletic field throws a discus. The height of the discus above the field in meters after it is thrown can be modeled using a quadratic function of the form f of x is equal to ax squared plus bx plus c, where x represents the horizontal distance in meters that the discus has traveled from the athlete. A specialized camera tracks the initial path of the discus after it is thrown by the athlete. The camera records that the discus travels through 3 points, 3, 282, 6, 4.25, and 9, 5.30, as shown in diagram 1. Use the coordinates 3, 2.82 to write down an equation of a, b, and c. So write down an equation in terms of a, b, and c. So what are they asking us? They're asking us for an equation, something with some equivalent sign, and they want us to write it down in terms of a, b, and c. The IB will rarely give information that isn't useful. They'll tell you about, like, let's say when the pyramids were built and so on, but after that they won't give you like inessential reading. So this first part, they told us that the height of the discus can be modeled by some quadratic of the form ax squared plus bx plus c. So we have this form of f of x, which is our output, is equal to ax squared plus bx plus c. And f of x, what is f of x? The height, right? So we can essentially almost call this h. F of x is our output, but the output itself is height. So we can almost call this the height. And we have these coordinate points. So we know after the discus has traveled a horizontal distance of 3, it's 2.82 meters in the air. When it's traveled a distance of 6, it's 4.25 meters in the air, and so on. So let's input these values into this function that they give us, and then we will have an equation in terms of a, b, and c. So an equation in terms of these variables a, b, and c, we see them in this quadratic, so let's Let's input and we'll get an equation in terms of A, B, and C. So height is equal to 2.82, and then A, we don't know what it is, but we know that the horizontal distance is 3 squared, or yeah, let's write it as 9 right away. So let's write it as 3 squared, plus B times 3 plus C. So now we actually have an equation in terms of A, B, and C. So this is one equation in terms of A, B, and C. There it is. One more question. Use your answer to part A and 2 similar equations to find the equation of the quadratic model for the height of the discus. Not a fan of this question, to be honest, because I think they are in some sense shoehorning or pigeonholing in some sense the test taker to solve it in a certain way, which actually I don't think is the most efficient way. So as a mathematician, if you're given some problem and you have a set of tools that you can use to solve a problem, you would probably want to use the most efficient way to solve it. And here they're asking, okay, well, write it out in a way that isn't actually necessarily the most efficient way to go about this. I'm not a big fan of that, but can save the complaints, I suppose. All right. So if we could do the first one and write an equation in terms of A, B, and C, we want to do this again 2 more times using these 2 other points, and then we want to use not polynomial root solver, simultaneous equations. We want to use simultaneous equations to solve. So let's go ahead and do that. So here's equation 1. Let's go ahead and find equation 2. Substitute these values. We know the horizontal height is 4.25 plus, and then we're going to have A times 4.25 squared plus 3, times B times 4.25 plus C, and then we can square that, 4.25 squared. Let's write it out. 4.25 equals, this is going to be, it's 18.0625. Decimals, we might want to preserve all of our decimals in this case, but let's write it out as 3 sig figs. 4.25 plus C. And the last one for number 3 is going to make use of 5.30 is equal to, and in this case we're going to be having A 9 squared plus B plus C. 5.30 is equal to 81A plus 9B plus C. So we've got these 3 equations. And now, with those 3 equations, we can use it to find the values of A, B, and C. So our function is given in terms of a quadratic, and this is the standard form of a quadratic, ax squared plus bx plus c. And if we know these values of A, B, and C, then we can fill in and find the equation of a quadratic. It's a similar sense to our equation of a line as y equals mx plus b. If we know m and b, then we have all we need in terms of the ingredients for an equation of a line. Here for a quadratic, it's just a, b, and c. And so how do we do this? I'm actually going to show you the easier way first. I'm going to show you the easier way. So this is a 3-mark question. It's an 8-mark question altogether. Actually, sorry, a 9-mark question. So you can potentially solve this using linear equations, simultaneous equations, but I'll show you an easier way to actually solve this. Okay, so let's go ahead back to the calculator screen. If we go into spreadsheets and we write our x values, our horizontal distance, and our y values, or the height, and let's put in the values that they give us. 3 and 2.82, 6 and 4.25, and 9 and 5.30. We have those values for horizontal distance and height. just like we need 2 values to find an equation of a line, we need 3 values to find a quadratic. So now we've got our values. Let's go statistics, stat calculations. Just like we did linear regression in the past, here we've got a quadratic. Our x's are in our x, our y's are in our y's, and there it is, a, b, and c. This is our quadratic. So I'm going to write this down. Where can we write it? To find the equation of the quadratic model for the height, I'll write it here. Y is equal to negative 0.0211. Make sure there's nothing else. 2111. That's right. X squared plus 0.667x plus 1.01. All right, there we go. Let's solve it how they would like to. Actually, use your answer in part A and 2 similar equations to find the equation of the quadratic model. So they're actually, if we have these 2 equations, to be honest, looking at the document once again, if we've got this first equation, the second equation, third equation, that's all they're asking us to do. And then they're asking us to find the model. I think that is actually the most straightforward and easiest way to find the model. But I'll show you how they would like you to solve it in a sense. What they're asking you to do, so far as I see, is they're asking you to solve a system of linear equations. So going back to the calculator, if we're at the home screen, menu, algebra, solve a system of linear equations. We have 3 equations in terms of x and y, and then we can put them in. That is to say, we have 2.82 is equal to 9x rather. This is a, b, and c. So 9x plus 3b plus, oops, I shouldn't do that, plus z. And to be honest, if you want to skip ahead, you can. I don't actually recommend you taking this path. X plus 4.25 y plus z, and then let's see, 5.3 is equal to 81x plus 9y. I just think there's a lot of ways that this can potentially go wrong. 2.82, 9x plus 3y, that's good. 18.1, 4.25 plus c. 5.3, okay. 2.82, 18.1, 81, x, y plus z. To be honest, I'll have to see. Let's see. So, here we go. This is me using a set of simultaneous equations, and to be honest, I've made some mistake here. The question using the first method of spreadsheets, just looking at the mark scheme, has given the correct answer. There's been some kind of input incorrect in here, and I can't say I'm particularly keen to try to figure out where. I don't think this is the most efficient way to solve this, and I'd recommend that you don't do it this way. But I guess maybe the one thing that's potentially helpful is linear equation solver, which you don't actually need to use too often, I don't think. I think spreadsheets is often a more efficient way. Okay, let's go back to the document itself. Okay. A 1.8 meter high wall is 30 meters from where the athlete threw the discus, as shown in diagram 2. Show that the model predicts that the discus will go over the wall. Find the horizontal distance that the discus will travel from the athlete until it first hits the ground, according to this model. Okay, so our model itself gives us a relationship between the height of the discus and the horizontal distance. So show that the model predicts that the discus will go over the wall. So we want to ensure that when we are 30 meters away, we're at least 1.8 meters high. So let's actually find the height when we are 30 meters away. So negative 0.0211, and this should be 30 squared plus 0.667, and this again should be 30, and this should be plus 1.01. Let's go ahead and work this out. 30 squared times negative 0.0211 plus 0.667 times 30 plus 1.01. And I've got a height of 2.03. Okay, show that the model predicts the discus will go over the wall. Really nice 3-mark question. Geez, that's just a pretty simple input-output question for 3 marks. I guess it hangs on whether the model itself was correct. Alright, find the horizontal distance that the discus will travel from the athlete until it first hits the ground. Again, we've got an input-output model, pretty generous, 2 marks. It depends on whether we've got the model correct. Here it is. So, find the horizontal distance, that is to say the value of x, where the horizontal distance traveled until it hits the ground. We know when it hits the ground. We know that h is going to be equal to 0 because there's no height. So let's go ahead and put an output for 0 and then negative 0.0211, and then this is going to be x squared. We want to find the values of x that are going to make this true. Plus 1.01. You can n-solve this, but the thing is when you do n-solve, it will give you the value that is closest to 0. So it'll actually give you a negative value, which would be incorrect because that's before time, really. So 2 ways to do this. Potentially graph it, and that would be okay. Or you can use n-solve and just feed it in a value after 1. Feed it, let's say, 1 or 5, and it will find the value to the further right. But I'm going to go ahead and graph it because I think that's a nice visual way to go about doing this. So, home screen, once again, negative 0.0211 x squared plus 0.667x plus 1.01. Alright, that looks good. Let's graph it. Zoom out. There we are. And then let's find, I want to analyze graph and find the 0. So at 33.1 meters, let's go back to the document. X is equal to 33.1 meters. When x is equal to 33.1 meters, we have reached the ground, which is good because it corresponds with this graph that they've given us, which is always nice, which is always reassuring. It means this extra little bit is 3.1 meters. And that looks about right. I mean, if it was 40 or 60 meters, tell us that something's maybe gone wrong. Alright, not a bad question, but the first quadratic question, or finding this as an equation in terms of a, b, and c, this was quite challenging. This is just spreadsheets. Linear regression, you need 2 values to constrain, 2 points to constrain a line. For quadratic, you need 1, 2, 3 points. So essentially you need a little more for quadratic, 3 points, and so on. Okay. This question right here, geez, this is another challenging question. Let's work through it. The diagram shows a map containing a long winding road passing a lake. The shape of the road can be modeled by the function r of x is equal to x plus 2 cubed plus 3x squared minus 2x. All distances in the map are in kilometers. The local hospital is located at point H, which has coordinates -2, 6. It's right here. To save time during emergencies, the local community is planning the construction of a bridge over the lake. The bridge will be built such that it is normal to the road at point H and will connect to the hospital at G. So once again, this is a pretty heavy algebra test so far. Somewhat uncommon, but not too bad, not too bad. It's good practice all the same. So we've got this road that can be modeled by this function right here, this winding road, and we have the hospital at point H, and we want to build a bridge. And the bridge is normal to the road at point H. And what that means is it's at a right angle to the function. So we know if we have some function, for example, and I'll write it in the corner here. If we have some function, and let's say a cubic function like this, we've got a tangent to the function, and then we've got something that is normal, that is to say at a right angle to this tangent line in this case. And that should help us out. So the first question is, using your graphic display calculator, find the value of r prime 2. So they're saying, hey, you don't need to take the derivative and do this yourself. We don't need to see the derivative. Just find r prime 2. That is to say, the value, evaluate the derivative at the point -2. So let's go ahead and look at the calculator. So we don't need to find r prime. We just need to find the derivative at the point -2. So a few different ways we can do this. I'll show you both. Easiest way is going to be algebra. Oops, sorry, not algebra, calculus rather. And we want to find the numerical derivative at a point. Variable is x, the value of 369. I've actually got to get a new document because it's a little cluttered. All right. Menu, calculus, numerical derivative at a point. We want to find the variable x, and we want to find it at -2, the first derivative. And now we have this notation, which is saying the derivative of what at the point x is equal to -2. Let's put a function in. It's x plus 2 cubed, whoops, plus 3x squared minus 2x, and we want to find it at x is equal to -2. There it is. X is equal to -14. So r prime of -2 is equal to -14. I'll show you the other way because sometimes it's actually helpful to do it this way as well. If you go on your calculator and put in the function as well, x plus 2 cubed plus 3x squared minus 2x. Here's our function. I'm going to zoom out just a little. And we want to find the derivative dy dx at some point. And so let's actually first get that point. Graph trace. Let's actually create a point. And let's set the point at x is equal to -2. A little cluttered. Let's move this over here. So we've got the point x is equal to -2. And now let's find the derivative dy dx at this point. And there it is once again, -14. This is kind of nice because you can do these things as well. If you go to geometry and you want to, let's say, find the tangent line, it won't give you the normal line, but it'll give you, let's say, the tangent at this point, which is -14x minus 12. So it gives us not only the slope of the line at a point, which is what a derivative is, but it also gives you the y-intercept. Means we're going to cut the axis right here at -12. But there it is once again. The derivative, that is to say the slope of this tangent line at the point -2 is equal to -14. Okay, good. Let's go on to part B. So going back to the document, it asks us to find the equation of the line normal to Rx at point H, which can be used to model the bridge. So we want to find this equation that is normal at a right angle to Rx. And remember, the IB rarely asks you something just as a piece of trivia. If they give you something, if they're saying find the derivative at this point, -2, the slope of a line of this function at a given point, chances are they're going to want you to make use of it. So find the equation of the normal to Rx at point H at -216. So let's go ahead and do that. I'm going to use this space over here. An equation of a tangent or a normal is going to have y is equal to mx plus b, or mx plus c. We need to find the slope. We know that the slope of the tangent is equal to -14. That means the slope of the perpendicular, if -14 is the same as -14 over 1, we can take the top and the bottom, or the numerator and denominator, switch it, and since it was previously a negative, we're going to multiply it by a negative, and this should be our new slope. So the slope of a line that is perpendicular, which is what the normal is going to be 1 over 14. Y is equal to 1 over 14 x plus b. We don't know what b is, but we do know a value of x and y that is on the line. So let's substitute x and y into this equation. Y is equal to 16, and x is equal to -2. And that should be enough for us to find b. So I'll just work that out. -2, 14, 1 plus 16. Okay. As a decimal, b would be equal to 16.1428, so on, or 16.1. As a fraction, it's equal to 113 over 7. So let's write it out. Y is equal to 1 over 14x plus 113 over 7. And if you want to write the decimal equivalent for both, that's perfectly fine as well. Just 3 sig figs. Alright. Now they want us to determine the length of the new bridge. 3-mark question. It's actually kind of a nice question, to be honest. I do like this question. Determine the length of the bridge. So we know how to find the distance. We even had a distance formula question above with those Voronois. The distance is just going to be, we can imagine Pythagorean theorem, it's going to be this distance right here. We know one coordinate point, but the question is, what is this coordinate point? What are the x, y values for g? And given that, and remember the IB often presents a kind of sequence of questions. Given that we have an equation of a line, and given that we've got a function, we know that one intersection point is at h. If we were to extend this through, there'd be another, but we don't need to build a road here. But if we look for the other intersection point of this line, it should be g. So let's go back to the calculator screen, and let's look at the function. So here's the function itself. We already plotted this point right here. I'm going to get rid of it and imagine as if we just have the function itself, as if we just graphed it. Let's go ahead and add the other function. So graph entry, let's put another function in, and let's put the one that we have. I don't have it as a decimal, so I'm going to use this value of with fractional values. 113 over 7. Okay. There's our function, and it looks pretty good. It maps what we have over here. Let's go menu, analyze graph. Let's find the intersection between 2 points. This one, if all things are good, should be at 216, and it is. That's very nice. Looks like we're in a good place. And here, this one shouldn't be dismayed that it's a not very nice decimal. So we've got a coordinate point, which is fantastic. So let's go back to the document, and let's put those values in. So we've got a point. We've got another point right here. And that point is, going to clear up some space. That point is negative 7.54 and 15.6. Okay, good. Now let's just find the distance. So let's write the distance formula out. Let's write it here. Distance is equal to the square root, this is given to you in your formula booklet, x2 minus x1 squared plus y2 minus y1 squared. Distance is, and then this is us just drawing out the Pythagorean theorem. This is going to be negative 7.54 minus, watch your negatives here, squared, plus, and this is me running out of space, 15.6 up to 16 is actually just going to be 0.4. So this is going to be a distance of, please excuse the shorthand, there it is, 0.4 squared. How did that happen? If you need to see, y2 minus y1, 16 minus 15.6. There it is. Okay. Here we go. Let's write it out. And negative 7.54 plus 2, square that value, plus 0.4 squared. Take the square root of all that business, and it gives us 5.55. I think potentially it is easy to get mixed up with the negatives, so just again, I do like these kind of intuitive explanations. Negative 7.54 going to 2, that means if we start at negative 7.54 and go up to negative 2, we've traveled negative 5.54. Similarly, if we're at 15.6 and we travel up to 16, these being both y values, that means this value right here is only equal to 0.4. 0.4 squared, negative 5.54 squared, and then you can use your Pythagorean theorem. Add those together and take the square root. Okay, and so final distance in the end is 5.55 kilometers. Alright, let's keep going. So far it's been pretty heavy algebra test, and the questions have actually been quite challenging, I gotta say. Now we're into some statistics. I think it's still actually a challenging paper, not gonna lie. Okay. Question 9. Miss Whitehouse is a chemistry teacher. After grading her final exam, she creates the following box and whisker diagram to compare the grades of her two classes. Identify which, we have class A and class B. Identify which two of the following statements must be true according to the box and whisker diagram. Indicate your choices by placing tick marks in the second column of the following table. Alright. The data for class A is normally distributed, which must be true, not necessarily the case. A normal distribution looks like this, and if that was the case, we would expect symmetry, and we don't see symmetry here, so not necessarily the case. No, there's two that have to be true. A higher percentage of students in class A received a grade less than 30. Higher percentage of students class A received a grade less than 70 on the exam. Higher percentage class A received a grade less than 70. So here's our 70 right here. So what do we know? We know that a box and whisker diagram divides things up into quartiles, where each of these sections is 25%. And what do we have here? Less than 70. It's possible that all 25%, it's possible that all of these students are right here, right? That, I don't know how large the class is, but we could imagine that all of them got a grade well below 70, that all of the 25% is clustered here. What we know for class A is that 25% and potentially at least one, right? Potentially they're all here, and then there's one person here. But we know that there's part of this 25% group got a grade of less than 70 by definition, or it wouldn't end here. So yes, this is true. A higher percentage of students in class A received a grade less than 70. More students in class B received a grade greater than 90 on exam than class A. more students in Class B received a grade greater than 90 on the exam in Class A. What do we know? We know the highest grade was in Class B. It has a higher maximum. But is it necessarily the case that more students in Class B received a grade greater than 90? This is a grade greater than 90. It's possible, remember each of these represent 25%, it's possible that we have all of these students right here getting grades of like, I don't know, 88 or so. And there's just one student here that gets a grade of 90, 98 or something like that. It's possible. And it's also possible that all of the students in this class, for example, since it represents 25%, all we need to ensure is that 25% of the data here is within this quartile. It doesn't tell us about how it's distributed, and we can't imagine that it's distributed evenly. We can't imagine that it's equal like this. It's possible that, for example, for Class A, that more students in Class A received a grade greater than 90, just based on the distribution. We don't know the distribution. We know that 25% is clustered here. This could potentially be a little higher. The interquartile range for Class B is less than the interquartile range for Class A. Interquartile range, Q3 minus Q1, here's Q3, here's Q1. This is smaller than this. Interquartile range for Class B is less than the interquartile range for Class A. All right. Not bad. There we go. At the end of the year, Miss Whitehouse surveyed a random sample of students from each of her 2 large classes to determine how satisfied they were with her teaching. Each student independently selected a value from 1 to 10, with 1 meaning that they were not satisfied at all, and 10 meaning that they were very satisfied. Her collected data from the student surveys is shown. Okay, so here's Class A, and here is Class B. Miss Whitehouse believes that there was no difference in the general satisfaction, so no difference in the general satisfaction between the 2 classes. She assumes that the data is drawn from population, normal distribution, and proposes to conduct a t-test for the 5% significant level. All right. So she wants to do a t-test. Normal distribution, this just means pooled is equal to yes, which it always is, by and large. I haven't seen one that wasn't. Pooled is equal to yes for our t-tests on AISL. Write down the null and alternative hypotheses. If we're calling this UA or U, we can call this U1 or UA. It doesn't matter. Let's call this mu A and mu B. Null hypothesis. Let's write it here, I guess. HO and H1 or H alternative. We're saying that this is the status quo, that there is no difference. And the alternative is that mu A does not equal mu B. That's our alternative hypothesis. Generous kind of 2 marks. Find the p-value for her test. Okay, we know it's at the 5% significance level. That comes later. Find the p-value. Let's go into the calculator screen and work this out. Go back to spreadsheets. Let's set a value for x and y, or Class A and B, and let's input the values. 7, 5, 3, 4, 3, 8, 6, 5. All right. And here we have 6, 9, 8, 10, 1, 9, 10, 9, 8, 3. So it doesn't matter that there's 2 more values here. Menu, statistics, stat test, sorry. And we want to do a 2-sample t-test. X is in our X, Y. Y alternative is the differences are, there is a difference in the average kind of satisfaction rating. Pooled is always equal to yes. Pooled is always equal to yes. There we go. Let's go down and find the p-values. Here it is. Okay, interesting. So let's go back to the document screen just in a sec. P-value 0.0952. Okay. So write down the p-value for the test. C p-value is equal to 0.0952 to 3 sig figs. Part D, write down the conclusion of the test, give a reason for your answer. So general structure for this, we write 0.0952, or our p-value compared to, where is it, our significance level. And in this case, our p-value is greater than 0.05. If you want, you can write this out as 9.52% is greater than 5%. And then what does that mean? Our p-value is greater than the significance level, so we fail to reject HO. Can you write except? To be honest, I'm not sure. I haven't received kind of clarification on whether you can write except. To be absolutely safe, fail to reject the null hypothesis. We can't reject the idea that there is no difference in this case. Or we, in another way, accept the idea that there is no difference. We fail to reject it. P-value greater than the significance level, accept the null hypothesis, or phrased differently, we fail to reject the null hypothesis. And this is our justification. Alright, let's keep going. So here we get into more statistics probability. Rita is playing a game. In the game, she must roll a fair six-sided die. I'm sorry, I'm just going to go back one sec and just to make sure that there was no context. Write down the conclusion of the test, give a reason for your answer. No, in this case it's okay. I was just thinking sometimes they do ask, for contextualization. In this case, there is no significant difference between the satisfaction between Class A and Class B. In this case, they just want us to write down the conclusion and give a reason. So here's our reason. This is the conclusion. Alright. Rita is playing a game. In the game, she must roll a fair six-sided die. If she gets a 5 or a 6, then she wins a prize. If not, then she has another chance, but this time she must flip a fair coin, which will result in the coin landing on heads or tails. If the coin lands on heads, then Rita wins a prize. Complete the tree diagram by writing in the 3 missing probabilities. Okay, so she plays this game. She must roll a fair six-sided die. If she gets a 5 or 6, then she wins a prize. So the probability of a 5 is 1/6. The probability of a 6 is 1/6. I don't know if we want to write a probability distribution, but probability of 5 plus probability of a 6. The chance that she gets a 5 is just going to be 1/6. The chance that she gets a 6 is going to be 1/6. So altogether, she has a 2/6 chance of winning. And a binary event, 4/6 chance of losing. Coin is fair. 50% she wins, 50% she loses. Remember, these two values must add up to 1. Find the probability that Rita does not win a prize. Alright, so if Rita doesn't win a prize, that means she doesn't win here, and she doesn't win here. 4/6 of the time, she doesn't win on the first, and then 1/2. Since these are independent events, we can just multiply along the branches. We have 4/12 or 1/3. So find the probability that Rita does not win a prize. P, let's write this for B. P, if we want to, this is her not winning, is equal to, and then we probably want to put this for method marks, but I'm going to write this out as 1/3. Given that Rita won a prize, so we're in the realm of conditional probability. Given that Rita won a prize, find the probability that she got a 5 or 6 when she rolled the die. Alright, going to go to the formula booklet for this one, and then we'll talk about this a little conceptually. Alright, where is our probability? Here we go. Statistics and probability. We have conditional probability under 4.6, third one down. PA given B is equal to PA and B over PB. And we'll talk about what that means. Alright, so here's our formula. PA given B is equal to PA and B over PB. So given that Rita won a prize, what happens? She wins a prize 1/3 of the time. Oh no, sorry, she doesn't win a prize. She does not win a prize 1/3. So what can we say? If she loses 1/3 of the time, since she can either only win or lose, we know that everything else must be her winning. So she wins 2/3 of the time. 1 minus 1/3 is equal to 2/3. This is her losing. She loses 1/3. She can either win or lose. The remaining times she wins, so she wins 2/3 of the time. So given that Rita won a prize, she wins 2/3 of the time. So we're in the domain of her winning. What is the probability that she got a 5 or a 6 when she rolled the die? So she can either win. She can win one way, like this. She can not win on the first, and she can not, and then she can win on the second. This is her winning a prize. The other way for her to win is this 2/6 of the time, where she just rolls the dice first. And if we want to find the total ways that she wins 2/3 of the time. What fraction of that 2/3 of the time that she's winning is made up of her just rolling the die? And she wins by just rolling the die 2/6 of the time. So find the probability she got 5 or a 6 when she rolled the die. So this is her 2/6. And that should be it. 2/6 over 2/3, which is equal to, is it 1/2? Let's see. It is. Equal to 1/2. And that should actually make sense. So twice as often she doesn't win, but half of this. If we were to multiply along the branches, this would be 1/3 of the time. 4/6 times 1/2 is equal to 4/12, or 1/3. And this is, of course, 1/3 as well. So half of the time. Total way she wins 2/3 of the time. What fraction is her winning just by rolling the dice? Well, 2/6 out of this 2/3 of the time she wins by rolling the dice. Alright, question 11. Nicole works at a local school 5 days each week. She drives an old car to work that has a 72% probability of starting on any given morning. The probability of the car starting on a given morning is independent of it starting on any other morning. So that's important. Independent, 72%. And then 5 days a week. Find the probability that Nicole's car starts on exactly 3 mornings in a particular 5-day work week. All right. So, interesting question. Interesting question here. Try to see where we're in, or what kind of domain we're in. We've got a set number of trials. We've got a set of independent events where the probability remains constant over a set number of trials, and we have a success or failure, a kind of binary event. We have probability of success or failure. This tells us that we're in the realm of binomial distribution. Set number of trials, independent events, probability remains constant, and we have success or failure. So we want the probability that Nicole's car starts on exactly 3 mornings in a particular 5-day work week. So number of successes is 3. In this case, successes are defined as her car not starting. Number of trials is 5, and probability of success, or probability of it not starting, is 72%. So let's go to the calculator and work this out. Menu, probability, we have distributions, and here we have a binomial distribution. Number of trials, in this case, is 5. Probability of success, we're defining success as her car not starting, which obviously wouldn't be a success for her. Lower bound is 3, and upper bound is also 3, because we want exactly her car not starting. Oh, sorry, this is her car starting. I'm sorry. Her probability that the car starts is 0.72. So it is a success. Number of trials 5, probability of success, her car starting 0.72. Lower bound is 3, upper bound is 3. We wanted exactly 3. There we go. So let's write this down for A. Binomial CDF. And we have 5, 0.72, and 3, 3. Okay. I think it's easier to stay within binomial CDF. Just remember your lower and upper bounds, and whether you're talking about exact or not. All right. Nicole walks to work on mornings when her car does not start and it is not raining. Nicole takes the bus to work on mornings when her car does not start and it is raining. Okay. Where Nicole lives, there's a 42% probability of rain on any given morning, independent of any other morning. The probability of Nicole starting is independent of the weather. Okay, wow. Find the probability that Nicole will not have to take the bus in a particular work week. So this is her not having to take the bus. Okay. So a lot going on in this question. For probability in general, it helps if we can write it out in some kind of diagram. In this case, since we have independent events, tree diagram should probably be okay. And what do we want to find? We want to find the probability that Nicole will not have to take the bus. Not have to take the bus. So she walks when her car does not start and it's not raining. She takes the bus to work when her car does not start and it is raining. So this is an interesting question. It's actually similar to the one before where we have this tree diagram where one of the branches actually stops in the end. So let's try to write this out from the very beginning and try to fill in a tree diagram. Often probability questions, if we can represent them graphically, they unfold a lot easier. So let's go ahead, give ourselves some space, and write out a situation. So her car can either start or it cannot start. It starts 72% of the time, and that means it doesn't start 28% of the time. Starts, she's good. She doesn't need to walk. She doesn't need to take the bus. And what is the case? If it doesn't start, she either walks or she takes the bus. So this is her walking. This is her taking the bus. She walks on mornings when her car does not start and it's not raining. So probability of her walking is equal to the car not starting, 0.28, times, so let's look at this. If it's not raining, a 42% chance of rain. So if it's 42% chance of raining, we can write P rain is equal to 0.42. And P not rain, of course, would just be 0.58. What's left over? So she walks to work when her car does not start and it's not raining. So 0.58. This is her walking, so it's sunny because it's not raining. And then when it is raining, which happens 42% of the time, she takes the bus. So whether she walks or takes a bus hinges on whether it's raining, which is maybe a little challenging to try to tease out what this question is asking. So find the probability that Nicole will not have to take the bus. What can we do? Not have to take the bus. This is her taking the bus right here. We can find the probability of her taking the bus, and then her not having to take the bus would just be everything else. This is her not taking the bus, and this is her not taking the bus. So we could do this. We could do 0.72, and then we could do 0.28 times 0.58 and add those up. And that's her not taking the bus. And to be honest, actually, that's not all that bad. So let's do that. 0.72, 0.28 times 0.58 plus 0.72. Okay, so this actually is equal to 0.1624, saving as much of our digits as possible, or levels of accuracy as possible. Let's write out the final value. So this is probability of not taking the bus is equal to 0.72 plus 0.1624. And here we have 0.8824. And if we wanted to be absolutely sure that this was the case, we would say, does this equal to 1 minus 0.8824? Sorry, it's 3 sig figs. We should round this. 82. And of course it does. 0.28 times 0.42. This is her taking the bus, and this is her not taking the bus. What's in red? So here we have it. Here's our answer in the end. This is a probability that she does not have to take the bus on a particular work week. All right, last question. Just about made it. Here we go. Thurston believes that more popular musical artists sell more albums. He begins to investigate this belief by randomly selecting 8 musical artists and collecting data on the number of followers each of the artists has on a particular social media platform. He then calculates data on the number of albums each artist sold in the first week after releasing an album, and then his data is shown in Table 1. All right. So we have number of social media followers in thousands, and number of albums sold in first week, also in thousands. Okay. As an aside, this is, this is the IB, I guess, trying to be relevant. Talking about number of albums sold. There's kind of like speaking at cross purposes, right? Social media and then number of albums sold. Potentially. I don't know if that is the most relevant metric in terms of artist sales and so. But anyways. Thurston decides to calculate the Spearman rank correlation coefficient. Complete the table of ranks shown in the table. So this is actually a 1-mark question. Spearman is usually 2. So what this is probably saying is that there's going to be no ties. If there was ties, then that would be one of the additional marks. So this is the highest, and then let's count down from there. This would be the second, this is the third, this is the fourth, this is the 5th highest, this is the 6th, 7th, and 8th. 1-mark question, reasonable enough. Okay, calculate the value of RS, Spearman's rank correlation coefficient. Not a bad question. This is very peculiar because this is the final question, which is often the most challenging. So let's go back to the calculator and let's put these values in on the spreadsheet. I think I'm going to need a new document. Okay. Here we go. Spreadsheet X and Y. These are the ranks for social media followers 4, 3, 6, 5, 7, 2, 8, 1. And we're going to pair each of these individual rankings with the rankings of the albums sold 4, 8, 3, 5, 6, 7, 1. So just remember once again, pairing the rankings with the corresponding rank of the number of albums sold in this case. So 4 pairs with 2, 3 pairs with 4, 6 pairs with 8, and so on. To find Spearman, once again, just like we would for Pearson's, except we input our ranks. So let's go ahead and work that out. Here we have our R value. So let's return back to the document. We see R is equal to 0.5952. Going back to the document. For B, R is equal to 0.595 to 3 sig figs. 0.595. This last question is very, very peculiar. To be honest, I've never seen something like this on a AISL exam. Here we go. Thurston believes that artists with a higher number of social media followers sell more albums in the first week. He carries out a hypothesis test using a 10% significance level with the following null hypothesis. In the population, there is no monotonic relationship between the number of social media followers and the number of albums sold in the first week. Monotonic means that they both grow with a growth in the x, we have a growth in the y, whatever those variables are. With the growth of the independent variable, we have a growth in the dependent variable, or just in two variables, I suppose. So potentially you could have something like this. As one grows, the other grows as well. A move to the right is a corresponding move to a move up. In this case, we're not asking for linear or anything like that. Just growth in one equals growth in another. As sales increase, so do social media followers. Social media followers increase, so do sales. This kind of thing. Not asking if it's linear. Write down Thurston's alternative hypothesis. There's no monotonic relationship. No monotonic relationship between the number of social media followers and the number of albums. So, assuming that this is no monotonic relationship, for the alternative, we would imagine that there is a monotonic relationship. Or we could say that there is a monotonic relationship, or we could say what? There is a correlation. There is a correlation. A positive correlation between the ranks of social media followers, between an artist's social media followers, and album sales. All right. The critical value of RS is equal to 0.643. State the conclusion of the hypothesis test given a reason. This is a weird question because it's not a t-test. It's not an independence or goodness of fit t-test. It's not a chi-squared test. It's a hypothesis test where he's comparing his Spearman correlation coefficient with, here we have the Spearman correlation coefficient with some critical value, that is to say some kind of cutoff point. And so the critical value of RS for this test is 0.643. The value that we found is equal to 0.595, and we know that this is less than 0.643. So in words, the strength of the correlation that we found was actually less than the critical value. If this is the critical value, it's the cutoff point. It's, let's say, the minimum strength required for us to say that there actually is some kind of relationship. So the conclusion for this hypothesis test, what could we say in this case? Conclusion for hypothesis test, if it's less, if the strength of this correlation, which measures the rankings between social media followers and album sales, is less than our critical value, 0.595 is less than 0.643, then there's not enough information for us to believe that there actually is a monotonic relationship. So in this case, we would accept HO, or once again, just to be safe, fail to reject HO. The strength of our correlation is less than at least the critical value, the minimum amount of strength. And so our null hypothesis, once again, is that there's no monotonic relationship. There's no relationship between social media followers and album sales. Alternative is that there is a correlation between the ranks. In this case, our value came out less than our critical value, so we fail to reject HO. All right, there we have it. I think that was the end. It is. Somewhat of a challenging exam, somewhat strange in terms of its structure, somewhat peculiar in terms of its emphasis, its algebraic emphasis. An interesting exam, I gotta say. Kind of enjoyable, I think, in some sense. And I hope it was helpful. Okay, everybody, take care, and best of luck, of course. Bye-bye.